going to talk about mirror symmetry for G2 nanoparticles. Thanks.
Hello. Thank you very much for having me. I'm very happy to be with you guys. And yes, I'm going to talk about this work. It's for mirror symmetry for G2 manifolds, which are built as twisted connected sums. And with the focus on those which are part of this class, which are built out of dual pursuit. I have to mention this is a joint work with Andreas Brown, which comes from the Mathematical Institute at the University of Oxford in the UK. You don't know him, here's a picture. And it's on the archive, and this is the archive now. Okay, so we can start. And indeed, dualities along the landscape of superstring compactifications are one of the most important features of the string theory. And among the non-dualities, the mirror symmetry for compactifications of type 2 on Calabi-Yau manifolds is indeed one of the most powerful. Full quantum duality is expected to give rise to an isomorphism for the whole quantum physics of mirror compactifications, which has a wide array of applications, from strings to homological mirror symmetry as far as the category of A-branes and B-branes are concerned, applications in field theory, like finding cyber-Hilton solution using mirror symmetry, using type 2B engineering for finding the analog of cyber-Hilton geometry. There are like plenty of applications. As a matter of fact, similar dualities have been conjectured for manifolds with special Coulomb, G2 and spin 7, long ago, in a paper 94 by Samson Chatterjee and Mubak. And in this talk, I'm going to survey a recent result that we have obtained about mirror symmetry for G2 manifolds. So let's J denote one such manifold, J stands for Joyce, and consider compactification of type 2 superstrings on J. In fact, one has a network of dualities, which we can represent as a square. So there is a horizontal map which sends a compactification of the same type 2 string to itself. And there is a vertical map. So the vertical map was conjectured by Papadopoulos and Townsend in 1995. And the horizontal map was conjectured by Acharya in paper in 96 and 97, generalizing the Strominger-Yans-Asdorf arc. So, given a pair of dual, a G2 mirror pair, J and J dual, one can relate 2A on J with 2A on J dual, and that one is 2B on J, and then propose with 2B on J dual and also a diagonal of this square, which are 10 compositions, which give rise to the relation between 2A and 2B in the universe.
What's happening to the cycles that we're interchanging? So usually there's this H11, H21.
So here we don't have a complex structure, and the thing is that J and J dual have the same V2 plus V4. But I will elaborate on this later. Then this talk will focus on H. And having an example of H, then of course allows you to do the rest. So the original formulation of the conjecture was in the context of appropriate to n equal to 1 superconformal field theories describing string propagating on G2 along manifolds. And then this n equal to 1 activities were given by Philip Barton in 94 and we should also look at the property of 96 where certain claims like here on the more start. So, as in the Calabi-Yau case, the origin of mirror symmetry from the CFT perspective is the presence of a non-trivial order 2 mirror automorphism within the algebra governing the theory. And for the Calabi-Yau case, this is a result by Odake and LPA. And for the G2, this was remarked in a paper by Reumann, Romes, Mergers, and Walker of 2002. And it was then made precise by Garavin and Castel. In particular, the case of this orbifold, the T2 mod C2 cube Joyce manifold, has been analyzed in great detail in the Gabriel cluster, and every map of the square of dualities was given an interpretation in terms of this weird automorphism for many dualities.
Can I think of the vertical maps as some kind of T-well?
All of them. In fact, all of the maps are dual. Yes.
But the horizontal ones don't exchange to
Because you have 40 dualities. As I will. So, as for the Keller modular spaces of Calabi-Gauss, the modular spaces of these 2G equal to 1 superconformal theories are generically larger than the geometric modular spaces. And indeed, the 2D theories have a conformal manifold which is dimension B2 plus B3, or B2 plus B4, where Bn are the petty numbers for the manifold J. And the equality follows from the fact that since you have just one on, you have a 7 dimension, and so B3 is equal to 4. So this is the modular space of the CFT. And therefore G2 mirror trace must satisfy this Satorshvili buffer relation. So that B2 plus B4 of J is equal to B2 plus B4 of J. And notice that this agrees with what is expected from the reduction of the 9 plus 1 dimensional type 2 supergraphs to 2 plus 1 dimensional and 2 only vector reserving for supercharges. Next, you see this is really controls the Recently, lots of progress have been made in producing examples of compact G2 Coulomb manifolds. And at least 50 million examples can be easily generated by means of twisted connected sums of asymptotically cylindrical Calabi-Yau manifolds. This is a result which dates back to Kovalev, but that was enhanced by a series of papers by Kortnik, Pachit, Hastings, and Nordstrom. And in fact, they were the ones who were able to exhibit this exorbitant number of examples, which motivates us to review, to revive the subject. Because before, the only known examples of compact G2 manifolds were just Joyce orbifolds and certain like trivial examples built out of Calabi-Yau's. Now we have and moreover, now, thanks to Simon's collaboration, more mathematicians are reviving the subject and more results are expected in the next few years. So it's the hot topic, at least for the mathematics community. The physical implication, of course, of this fact are stunning because each of these examples corresponds to a valid compactification for MTO. Of course, the examples constructed by mathematicians are smooth. We are interested in singular ones because we want to build H theories. But, I mean, it's the same as for Calabi-Yau's. Also, constructing Calabi-Yau metrics which are singular is kind of tricky from a mathematical perspective. We are there because there are degenerations. In particular, it is very natural to ask about G2 mirror map, this context happens of this. And this is the subject of this talk. So let us begin with a quick informal review of the construction of this twisted connected sub G2 alone. So we consider a pair X plus and X minus of Calabi-Yau trifolds, which are asymptotically cylindrical. What does that mean? It means that they have a corner which asymptotically has the form of a cylinder times a HET surface. So if you wish to be more precise, we have a manifold X plus, which has a compact subset that you can remove from it. And that outside this compact subset looks like asymptotes to a K3 vibration of an interval. And this is a plus, and this is a Y square. Okay. And you have two of them. Now, in particular, the metric can form a holomorphic top for a Calabi-Yau of this sort, or in the asymptotical Calabi-Yau cone cylinder, converges to metrics of this form, which are controlled by the the metric, the Keller form, the top form of the K3 fiber behaves very nicely with respect to the asymptoticity. Okay. And now we want to consider these products. We want to add an extra S1. Then here we put the other caveat facing this. So on that side, it's minus. This is symptotic fiber. This one is the other reference. It's minus. So we consider these products. And each side can be separately equipped with a G2 structure, which is built out, which asymptotes on the cylinder. In this case, no, this is the core thing. Each side can be separately equipped with a G2 structure, which has this form. So psi is a coordinate on the extra S1, and then these are the Keller form, the top form of the trigon. And now we want to consider the asymptotically cylindrical regions, and we want to fix a positive L and consider an interval. So here you see this extends to infinity, which you see this one, right? We want to fix a finite L here and consider a time interval here, right? And the same what to do here. And essentially, we want to truncate the cylinder so that we let them asymptote until they reach the stable form that we like, and then we truncate them. Consider this interval, and we want a diffeomorphism which is valid on the interval, and it is such that it allows to pull back the G2 structure from one side to the one of the other. Okay, in such a way that we can glue these two to form a G2 metric. And in local coordinates, this diffeomorphism is given as such. So you can see that it switches the roles of the two circles. So I'm taking this circle and I'm mapping it to this one, and this circle and I'm mapping it to this one. And it is also shifting T. So I'm taking this point and I'm mapping it to this one, and so on. Right? And then it acts on the K3 fiber in an interesting way. So G is a map from one to the other, which is a hyperkeller rotation. What is a hyperkeller rotation? It is a diffeomorphism of K3 surfaces, which induces the following actions. So it preserves the metric, but it pulls back the real part of the top form of the K3, and it switches with the Keller form, and it changes sign of the imaginary part of the top form. Okay, so the real part of the two top forms gets swapped with the volumes, and the imaginary parts change sign. Okay, this is why it is called a hyperkeller rotation, because each of these three terms can be viewed as a triplet. We have a hyperkeller structure.
Wait, so G is a map
from S plus to S minus. And it's such that was you pull back stuff from S minus in this. Okay.
So are there conditions then on S plus and S minus such that this kind of happens?
Yes, it's a condition on the structure of the two asymptotic cylinders, the existence of such a map. And now truncating both manifolds at equal to n plus 1, one obtains compact manifolds with boundaries, which are S1 times S1 times S plus minus, that can be then glued using this diffeomorphism. Okay? And if L is sufficiently large, the manifold J so obtained is a G2 holonomy manifold. And this is a theorem which was proved by Corti, Bacini, Haskell, and Norton. the resulting method is called the twisted connected sum of these two. It is twisted and connected because you are twisting the S1. Notice that if you don't do this twist, if you don't identify these two sides, you end up with something that has a pi1 which is infinite, and this is in contradiction with the fact that you want the G2 holonomy method.
If you don't do what?
If you don't do this twist, you get a P1 which is not clear. And you need that for having special rule.
Is this what you get here? Is this like, can you generate like a family of this Ptolemy manifolds, families, right? Or
Yes.
this other point in all these?
Well, like, you want L to be sufficiently large. But apart from that, which is like one of the moduli, the rest of the moduli x plus x minus are free.
Okay,
So if you wish, it is a codimension one condition of the moduli space of the whole thing. And I don't know if there are like, that is something that I wasn't able to extract from the math literature. I will ask them. I mean, I expect that like going from reducing L to be smaller and smaller and smaller, you can get like neighborhoods in which the G2 metric can be approximated better and better, but that is unclear. I don't know if you get to a G2 holonomy metric in the limit where L is infinite. And when you start making it smaller than infinite, you get something that is not G2 holonomy. It means like something weird, like something like breaking supersymmetry when we couple gravity, right? And that is, I don't know. I mean, it might be interesting, it might be not, might be stable, might be unstable. It's open, and I don't really understand it. For the moment, I think that this is a codimension one condition in the moduli space. But that sounds weird. Probably, I don't know. The status of the art on the mathematical literature is this one. You need this L to be large.
But couldn't there be other compact G2 manifolds that just can't be approximated by this kind of construction?
Yes. Yes. No, the only thing is that, look, before there were like 20 examples, now there are 50 million.
But I'm just saying you can't say it's codimension one. Because you have no idea.
No, it's codimension one in the modular space of this guy.
These
Not in the
types.
space of the whole G2. No,
Yeah.
it's just on this guy, you need to tune a modulus to find the G2 metric. Which may be interesting. I think it's like, if it is true that there may be some interesting physics there, but maybe it is broken by quantum corrections. So this is all classical, if you wish, from the perspective of Zotto. So just,
You really only need this for the proof though, is you need to show the existence of some solution to a differential equation for a long enough time. But
yes.
it's sort of like never really a problem. Right?
Yes. I think so. In fact, I mean, I think this can be broken. But, if you want to be very
I
safe.
mean, it's not like this construction has to have long necks.
No.
At the end of the day, it's just
Well,
used to show that you have such things that.
that is something that I wasn't able to extract from mathematician yet.
Okay.
I mean, they disagree. Like, somebody says, yes, you need to have this domain. Somebody else does. So, I'm still there. I don't. But for the moment, like, it's fine.
It's
I
just
agree with
the
you.
usual neck in the Ritchie flow, right?
Yes.
You just don't want it to pinch, and you have to make sure that doesn't
That it
happen.
flows over.
Otherwise, you have to start cutting and doing things like this.
Just to make sure I understand, the G2 holonomy requirement comes because you chose that very, very specific discrete rotation. Okay. So like, so if I had chosen, anything else, I would have gotten just, a much more generic interval.
Yes, you need to, like, that is part of the data. Like the doing diffeomorph is part of the data that defines your twisted connected sum. And in particular, like given 2x plus and x minus, there may be several inequivalent ways of doing that, which are still giving satisfying definitions. So it's like giving the two sides doesn't uniquely specify the G2 manifold when to need also to specify this group as a word. So now, one heuristic way of approaching the G2 neurosymmetry story is given by this generalization of the S1 arc. Let me review this. So G2 holonomy have two types of calibrated submanifolds. They have associative submanifolds which are calibrated by phi, and co-associative ones which are calibrated by the dual phi. Now, these have deformations, and associative submanifolds have deformations which are abstracted, while co-associative submanifolds has deformations which are unobstructed. So in particular, any co-associative submanifold of a continuum G2 manifold has a smooth modular space of dimension B2+, which is the number of self-dual harmonic two-folds on this submanifold. This is important for us. So let's consider a putative G2 mirror array and consider a compactification of 2A on these guys. The zero brane has a modular space which is equal to J, and we are just repeating the extraordinary argument, which must correspond to the modular space of a wrapped DP brane on J2. Right? And since we want a VPS configuration, we must wrap a calibrated site. And the only option left, since the associative ones are abstracted, is a co-associative. Because we want it to be something there. And we want to wrap a co-associative with a default brane. So the U1 vector field of the brane will give rise to V1 additional moduli. And so the physical modular space will have dimension V1 of n plus V2 plus. Okay? And for this to coincide with the D0 brane, the modular space must agree. And in particular, you need to find a co-associative submanifold such that these two add up to 7. And T4 has this property, because the Betti numbers of Tn, if you wish, are just the binomial coefficient. In the case the Betti number is an over k. Right? So it is natural to conjecture that we have one such n, and that n is a T4. And this is what the Acharya did. Now, in our case, we can build such T4 co-associative federation. So extend this Stromming derivatives to this case leads to this horizontal mapping that you need for symmetry. In our paper, we present a heuristic argument to argue that this is indeed the case for these twisted connected sums. Okay. So the main idea of this heuristic argument is that one can glue the special Lagrangian Stromming derivatives vibration of the symptotically cylindrical between blocks into a T4 co-associative fibration of J. Then the G2 mirror manifold is obtained by 40 dualities along this T4 co-associative along the lines of the original SOT.
Can you hold on a second?
Yes.
Catch me up.
Okay. So, but I will elaborate on this. So, why such gluing is possible? Why such gluing is possible because by construction, the co-associative calibration is also preserved by this gluing diffeomorphism. And so, if you look at the explicit expression for this and you can of course rotate the top form on the Rabian because you're free to multiply them by complex number. And you can rotate them in such a way that the Stromming derivatives or special Lagrangians are calibrated in this way. So that the restriction of that is minus I of the volume of the special Lagrangian file. If you do that, then S1 times this special Lagrangian within the threefold becomes a co-associative, becomes automatically calibrated by star phi plus. And the compatibility condition above this one does the rest of the job. So you can take these two co-associative on this side and on the other side of the construction and glue them together into a co-associative T4 file. It can be seen, right? But that is not an issue. So in particular, along this Cabiau cylinders, this SOT fibers will asymptote to S1 times the SOET fibers for the K3s, right? So we propagate, and here it will wrap 1s1, and then the rest of the special SOET fiber will be inside of these two. And therefore, when we perform the dualities, we will induce mirror maps also on the asymptotic fiber, swapping S plus and minus with the mirrors. Okay. So the result, the result is that when we perform these 40 dualities, we are swapping X plus and X minus with the mirrors, and we are swapping also the Lagrangian fibers, the K3 fibers on the asymptotic Calabi-Yau cylinders with the mirrors, and we are gluing. What it is missing is the gluing data, whether it is fixed uniquely or not by this construction, and there is indeed a way of finding that as well. So it suggests a canonical way of extending the hyperkähler rotation to include the B field. If you extend the definition of this in this way, then it's elementary to check that the composition of the mirror symmetry with this gluing, with this extension, plus another mirror map, satisfies the definition of hyperkähler rotation. Okay. And therefore, like since this is canonical, it's natural to expect that this is the right gluing to assign to this twisted connected sum. So we find that the mirror G2 manifold G2 was obtained is a twisted connected sum of the mirror asymptotically significant between blocks. And moreover, the asymptotic Calabi-Yau cylinders must have this structure, where this is a T2 cycle, and this is a mirror of the S plus and minus as K3 surface. Now, of course, there are lots of subtleties in this heuristic argument we are not addressing here. And these are in part related with the subtleties in the original SOET argument, which requires to be a specific point in the model space of the Calabi-Yau. And also go beyond, because now we have all these singularities related to this twisted connected sum. But this argument, this heuristic idea, is meant to be no more than a motivation to look for examples of G2 mirror pairs with this structure. Can we find examples of mirror pairs that satisfy this, such that the two sides are Calabi-Yau, asymptotically significant Calabi-Yau manifold are mirror to each other, they have the necks over which the K3 fibers are mirrored to each other, and there is a gluing which is defined. Is this a dream, or are there examples? And remarkably, precisely this structure emerges for G2 manifolds that are twisted connected sum of asymptotically cylindrical Calabi-Yau triples constructed from dual tops. So here, this is the extra ingredient that we need to find explicit examples of this variety. So this is not a surprise, because in the Calabi-Yau case, the larger class of examples of Calabi-Yau manifolds for which a mirror is readily constructed, and in fact, the largest class of examples of Calabi-Yau manifold is given by Calabi-Yau hypersurfaces and complete intersection in toric varieties. And these G2 manifold twisted connected sum which are built from dual tops are essentially the analog thing for twisted connected sums. And in this case, the construction rests on the polar duality between reflexive points. I think that everybody here is familiar with this picture. Okay? Where mirror symmetry just see reflection with respect to the sizes. And our main result is precisely the structure analogous to that of the Butterworth mirror map is in place for G2 manifolds that are twisted connected sums, whenever these are built out from pairs of dual tops. And the G2 mirror pairs are canonically obtained by just switching the roles of the dual tops using the construction. So this depends on a pair of tops, and you just swap them, and you obtain another G2 manifold which has exactly the structure predicted by this heuristic argument. In particular, indeed, we find that by switching the dual tops in the construction, we obtain G2 mirror pairs that have this structure, and they are twisted connected sum respectively of X plus and minus and their mirrors, and the asymptotic Calabi-Yau cylinders are K3 fiber by mirror pairs of K3s. Moreover, in this case, we are able to show that the pair of G2 holonomy manifolds obtained indeed satisfy this Shapashvili buffer relation.
The dual top keeping track of your hyperkähler rotations?
There is a later I will be more technical. It's going to be more technical, but the point is that yes, the hyperkähler rotation boils down eventually to a condition on the Picard lattice of the K3 surfaces of the two fibers. So you are training the whole differential geometry for lattices. Once you do it, and therefore yes, you can literally see on the lattice what is the effect of the gluing and whether some gluing is possible or not.
Is the idea that the K3s are all isomorphic, so you can just have a classification that comes from what classifying the hyperkähler rotations of K3s or K3 structures?
Well, but here you see you want this K3. So the real thing that we are classifying are these stops, which are a tool to build the K3 fiber at the trifolds. And then, like out of this K3 fiber at trifolds, you find a condition to obtain K3 fiber at asymptotic cylinders. And that's once you have that in place, then you start placing condition on the orthogonality relation of the various lattices, which amounts to the choice of a hyperkähler rotation. So we are able to show that they satisfy this. We construct various millions of examples of these pairs, some of which are explicitly discussed in the paper. And moreover, the Calabi mirror symmetry also intensely isomorphic of these two lattices, right? And it is natural to expect an analogous phenomenon in the context of these two mirrors. And in our case, what we find is that the H2 plus H4 are preserved under this mirror mass. So also the torsion against these two cases. And the case of H2 plus H3 is in progress because in the examples that we have checked, and we have checked like I don't know 4 or 5, it's not that many, this match, the torsion also of this match. But speaking with Joyce, like he said that he expects that the fact that this matches is not as natural as this. So for this case, we're still like in progress. We don't know whether it's.
Those are the guys that are obstructed, right?
Well, the co-associative manifolds are abstract, which is exactly the reason why you expect that can be subsided. So in the rest of the talk, I'm going to give an overview of the method that we have used to establish this result, and then sorry, it's going to be a bit technical.
Okay, just so I understand, know that I'm following. So your dual tap is going to also encode the asymptotically cylindrically K3 property of the Claude-Gall. Because it has to somehow relate things like H21 to the H11 of the K3 and things like that. The dual tap will already have that.
Yeah. I will just discuss it now. So the thing is that in order to build this DCS, one of the key points for Haskins was using these building blocks. Building blocks have trifolds, which give a very elegant way of producing examples of asymptotically cylindrical Calabi-Yarrows, which are needed in the DCS construction of G2 mechanisms. So then TOPS gives a very systematic way of building examples of building blocks. Okay. So first I will review what building blocks are, and then I will review what are TOPS, and eventually the result. So a building block is a fibration, it's a trifold which is a fibration over P1, okay, whose generic fiber is a non-singular K3 surface. It satisfies some further technical assumptions. So the thing is that now, see, in a sense, the idea is that, okay, so you have a P1, and with this P1 you have smooth, generically smooth fibers, okay? And now there are certain technical assumptions that test me that I can remove one fiber and then deform this into an asymptotic cylinder, which is Calabi-Yarrow. Okay. So with these asymptotes, that's plus there. Okay. So the technical assumptions are the following. So there's a condition that anti-canonical class of dead, which essentially says that it must be primitive, and that you can that if you remove one fiber, you get something which is radial. And then it says that you have an asymptotic which has the form that you like, and that you can map the lattice of this guy into the pickup lattice of the K3 file. Then, denoting the image of this restriction by n, you want also that this quotient, the gamma 319 is the modular space of the K3, and you want that this quotient distortion, so that this embedding is primitive, in such a way that you can just discuss everything within this lattice. Also, you require that this guy has no torsion. Under this assumption, it follows that this building block is simply connected and has all number H10 and H20 that vanish. Since T is a K3 fibration where P1, the non-bound bundle of the fiber, in particular of S0, is trivial. Okay, so it's really. Now, the fact that this lattice embeds into the pickup lattice of S0, and that we can think of the fibers as being element of a family of lattice polarized K3 surface, polarized lattice L. So, what is the point? Yes, the point is that we can think of the fibers really like as being elements of the family of lattice polarized K3 surfaces, which means that like when we discuss mirror symmetry in this context, we are going to discuss mirror symmetry for this type of K3s, not for the whole K3. I mean, we are not going to take, like, we are fixing a complex structure. The K3 mirror symmetry, if one includes also the possibility of doing hyperkähler rotations of the various complex structure for the K3 is larger, but we are fixing it. And so by excising a fiber, we can form this open space, and this open space is an asymptotically symmetrical reality. Now, building blocks are extremely useful technical tool for completing this. And the geometric data encoding the gluing translate into combinatorial conditions about the embedding of this lattice of the two building blocks inside the pickup lattice of the K2 surface. And in particular, these are completely determined. So there are explicit formulas for computing all of these lattice in terms of the various embeddings, the complements of them, and the kernel of the map row. The map row is the embedding of the H2 lattice within the lattice. So everything is under control. And now that this is in place, let me proceed reviewing what are the stops and how we can use them to build some good blocks. So a pair of lattice polytopes which satisfy this condition are reflexive and define a Calabi-Yau manifold embedded as a hypersurface in a contour. Okay, this is the usual story. In this construction, the polytope delta is the Newton polytope giving rise to all of the monomials of the defining equation. In the polytope delta dual, the polar dual, after an appropriate triangulation defines the toric ambient space. Now we want similar things for building building blocks. Okay? And this is done by using pairs of four-dimensional projecting tops. So top is defined as a bounded lattice polytope, which satisfies this condition for a set of limit lattice at this point. And the last relation, this one, defines a hyperplane. And one of the conditions is that the intersection of this top with the hyperplane is a reflexive polytope. Okay? We're calling it F because this is going to define the fiber. Okay, so you have the lattice. The lattice is specified by these two conditions. One of them, like canonically gives to this lattice the structure of a fibration. And indeed, tops naturally appears as halves of the reflexive polytopes, which define Calabi-Yau hypersurfaces, which are fibered by a hypersurface of one dimension longer, which is defined by this reflective plane. This appears in the mathematical literature and used in the context of heteronomy, magnification by Canela Sanford in the 98. So the idea, I don't know if you're familiar with this, but if you think about the half K3 surface, if you have a K3 surface, you know that you can degenerate it into a pair of dp9s. Okay? And this is essentially the same thing but in higher dimensions. You start with a fourth fold, which is a vibration over let's say an n-fold, which is a vibration over an n-1 fold. And you can degenerate it, and the things in which it degenerates are not themselves Calabi-Yau, as in the case of the K3, which degenerates in the 2D things, but still has lots of structure. So in our case, N and M, these two lattices are four-dimensional, and we can always exploit this to fix and zero this lattice vector. And then a projecting top is one such that when we forget the fourth coordinate, maps this lattice within the dual polygon corresponding to the file. So these are precisely the guys that we are going to use, and for any of such polygon, there is a dual top which satisfies this, and this is the correct notion of duality in the context of top, which replaces the polar duality that was used by Battier in the construction of Calabi-Yau mirror layers. And as a convex lattice polygon, this defines a toric variety as well as a line bundle on it. And a section of this line bundle defines the hypersurface that we want, which is given explicitly. And for a projecting top, these two are a reflexive pair, which means that this is the hypersurface, that this hypersurface, the labeled by this pair of dual tops, dual projecting tops, is fibered by a K3 surface, which is defined by this reflexive pair. So you have everything under control, just doing intersection of lattices. Okay? And now, Calabi-Yau mirror symmetry for hypersurfaces within toric varieties is just realized by swapping the dual pairs. And again, in our case, we have a G2 manifold, which is a twisted connected sum of asymptotically symmetrical threefolds. And again, in this case, the G2 mirror of it is a twisted connected sum of the asymptotically symmetrical dual Calabi-Yau threefold, which are obtained by swapping the tops. Okay. And what is remarkable is that using this construction, we are able to give explicit example of the structures we conjecture based on the Sweaty vibrations. Now, notice in particular that indeed one obtains automatically asymptotic Calabi-Yau cylinders which are fibered by the mirror K3s in the asymptotic region. And in particular, the fibers of the mirror building blocks are from algebraic mirror families of K3 surfaces. So then, by using the various relations here, using these explicit examples and the various lists in the papers by Catenas and Font, we wrote a Sarge code which generates these examples automatically. And we were able to check that indeed these two lattices agree for mirror pairs constructed in this way. And
What are they called, tops?
Yeah, because when you what is the idea? Because you are splitting a K3 fibered threefold right into two parts. One is the top and the other is the bottom. And another fact is that indeed, like to see that these are that there is this mirror symmetry in place. The main thing is so you have this thing which is like fiber over P1, and you have your K3 fibers on it. And you find that the generation in which this essentially splits, right? Here it pinches somehow. And this is say, to reach the top, and this is the bottom.
So it's the analog of the deep lines.
Exactly, it's exactly the analog, right? And what is remarkable is that in this case this is a threefold. So you have the Butler mirror map in place, and you can explicitly construct the mirror of this guy. And by doing the degeneration of the mirror of this guy, you see that it gives rise to a structure which is analog of this one, which has the structure of the mirror feathers. And so in this case, if you wish, you get your Z associated to this pair of tops. And if you do the generation of the mirror, you get the one corresponding to the one which has the tops swapped. So in a sense, as a side application, we are also building like a candidate for mirror symmetry for these building blocks. Right? Essentially, the statement is that the mirror G2 manifolds are obtained by gluing mirrors of their building blocks. Now, so our work, this work, is bringing evidence for this G2 mirror symmetry conjecture, because before the examples on which it was checked, it was just this 7 model, these 7 orbifolds by Joyce, and that was very precise. This paper by Gabriel and Casting, which I referred to. And now we have a plethora of candidates, conjectural examples of those, which is analog to what I think the popular mirror symmetry one.
Can you also say that your construction guarantees that the G2s you generate do obey the mirror symmetry conjecture? I mean, it could have been, for example, like Henry was asking before, that you're missing huge swaths of the G2 sort of space of G2s.
Well, you see, the way that we want a map which is order 2, so that if you apply it twice, it gives back the original one, and that it satisfies this sort of really buffer relation, plus we have also this requirement of the lattices. And that more or less fixes uniquely, as far as these G2 manifolds, which are twisted connected sum, are concerned, that fixes uniquely how that has to work. Of course, I believe that there must be examples of G2 manifolds which are not twisted connected sums, and examples of this sort are indeed within the class of Joyce orbifolds, I think. But I think that more are going to come. And for those, the mechanism underlying the G2 mirror symmetry is going to be different. I expect there is going to be a story also there, but since those examples do not exist already, the story needs still to be figured out. So we have constructed several millions of novel examples of G2 mirror pairs. But there is still lots of work to be done. So first of all, it would be extremely interesting to understand what is the sigma model version of this law, right? Because like each x plus and x minus have a 2D2,2, if you wish, counterpart. And like the idea behind the twisted connected sum is that you can take two manifolds, glue them together in a funny way, and get a G2 manifold that should be somehow mirrored by the idea that you can take two 2D2,2 models and find some sort of gluing among them, which preserve only a common n equal to 1 subalgebra, which ends up being the n equal to 1 Scherzer buffer. And so this is one thing that needs to be made more precise, because what we have done is just constructing explicitly these examples using algebra geometry. There is a whole chapter about this, which is related to topological G2 strings. They have been constructed by De Boer in 2002 and so on. And like, I mean, it would be extremely interesting to see whether there is an analog of the AMD model story in this class of models, or this class of models. What happens to brains? Like, we have seen that these D4 equalities, you know, that there is like zero maps not specific before, but what happens to the rest, it's unclear. Whether there is like a homological mirror symmetry version for G2 manifolds, it's unclear. Like, all of this needs to be worked out. And also application within supersymmetric field theory are in the run, because you see, if you compactify a theory on one of these G2 manifolds, you obtain a for n equal to 1 theory. You have a dual, you can reduce both on circles, and you end up with 3D theories. But the 3D theories that you obtain are identical because of this mirror symmetry, while the M-theory compactification are inequivalent, because the M-theory moduli space depend only on B3, not on B2 plus B3. And so, like, you have examples of models which become equivalent under silicon reduction. So this, of course, like for the theories that we are considering, like in these smooth examples, is obvious, right? Because it is just amount to the fact that in 3 dimension, scalars and vectors are dual, right? So if you have something which is smooth, you have just U1. Yes, they just become exactly. You can dualize scalars to vector, while you cannot in 4 dimensional. For non-abelian cases, that becomes more interesting. And it becomes also more interesting if you can like conceive to construct to degenerate this twisted connected sum in such a way that you can coalesce several singularities to something which is not trivial, like to a superconformal point, if you wish, on the modular space of this matrix, corresponding to some, I don't know, to some discrete subgroup of G2. All of this is still like work in progress, and there is lots of work to be done. Also, another interesting remark, is that G2 manifolds are 7 dimensional, so they have only a character which is 0. And so essentially that implies that whenever you have a parallel spinor, you can build other ones. So you would expect that these systems have an enhanced supersymmetry which is broken. And that more or less matches with this picture of the glue. Because you have like an enhanced supersymmetry on the neck, which is given by the K3 surface times S1. And then, in a sense, if you degenerate this to be infinitely long, you're breaking the boundary conditions corresponding to X plus and X minus. And also, this is like work in progress. So, stay tuned. Thank you for your attention. And